Hello, my name is Hyunjun Kim, and I'm going to talk about new subgraph query processing and subgraph matching algorithms by using versatile equivalences in a graph. This is showing work of Seoul National University, University of New South Wales, and University of Sydney and Postec. The problem we've studied in this paper are subgraph matching and subgraph search. So I will show the overview of our algorithms briefly, followed by the details on three main techniques. And I will show the performance evaluation, comparing ours with state-of-the-art method, and we'll conclude the presentation. For simplicity, we consider only graphs, undirected graphs with labels and vertices, but our approach can be extended to more general graphs. Given a query graph Q and a data graph G, embedding of a query graph in a data graph is a vertex mapping M such that M is injective. For every query vertex U, its label is the same as its mapping's label. For and every edge in a query graph, there is a corresponding edge between mapped vertices in a data graph. So subgraph matching is to find all embeddings of Q in G, which is NP hard. In this example below, there is uh, one embedding of Q in G, which is depicted as red subgraph here, and also we can find another embedding of Q. So there are two embeddings of Q in G, uh, which are what we are going to find uh, for this problem as an output. Given a set of data graphs D and a query graph Q, subgraph search or subgraph query processing is to find all the data graphs in D that contain Q as subgraphs. So in below three data graphs and one query graph, the only data graph that contains Q as a subgraph is G3. So we output G3 as an answer set for this problem. Since subgraph matching and subgraph search are fundamental problems in graph analysis, they have many applications such as social network analysis, protein-protein interaction networks, and chemical compound search. So much work has been done to efficiently solve these problems, but existing methods have some challenges. For example, indexing filtering verification approach build an index from data graphs, and when query graph is given, they use an index to filter out unpromising data graphs. So, but indexing method were shown to be somewhat inefficient in terms of filtering power, indexing time, or indexing space. And existing method also suffer from suboptimal matching order and redundant computations in search. So generally, previous method use a, a backtracking framework which consists of two steps. First, they adopt a filtering process to find a candidate set for each query vertex U, where CU is a subset of data vertices which U can be mapped to. In the example above, U1 in a query graph can be mapped to V1 or V2. So we build a candidate set of U1 as V1 and V2. Next, they choose a linear order of query vertices called matching order and apply backtracking based on this matching order. Suppose that we've decided matching order as U1, U2, U3, and U4. Then in backtracking, we first map U1 to V1, U2 to V3, and U3 to V5, and so on. So our algorithm called back also uses this backtracking framework, but with different techniques in detail, which result in a much faster algorithm. This is overview of our subgraph search algorithm. So for given a query graph, we build a query deck from that query graph. And between this query deck and every data graph, we perform dynamic programming together with a filtering technique using a new concept called neighbor safety. And the output of this dynamic programming is an auxiliary data structure called CS, which consists of a candidate set for every query vertex and adds between candidates from different candidate sets. And given this CS, we perform backtracking, and in this backtracking framework, we propose a new matching order based on equivalence of query vertices and uh, runtime pruning technique by pruning equivalent subtrees in a search tree by using equivalence of candidate vertices in runtime. So this algorithm finds up to one embedding of query graph in a data graph, but this can be easily modified to run subgraph matching to find all embeddings of Q in G. So given this query graph and a data graph, we build auxiliary data structure called candidate space or CS, and it consists of candidate set for every query vertex and edge between candidates from different candidate sets. So how do we get this CS? What we propose in this paper is the way to get more complex CS by using our filtering technique by uh, neighbor safety and dynamic programming, which is already proposed in the previous Sigmod paper. So for filtering by neighbor safety, we for every vertex, query vertex U and its candidate vertex, uh, we compute use neighbor with the on every label L and voice neighbor in CS with every label L. So if the number of V with label the number of neighbors of V with label L is smaller, then if such label exists, then we say V is not neighbor safe regarding U. So in this example, let's say we are given U2 in a query graph and V3 uh, as an U2's candidate vertex. Then for label L, U2 has two neighbors, U1 and U4 with label L, while V3 has one duplicate neighbor, V1 with label L. But mapping U2 to V3 will lead to no embeddings because it U2's neighbors U1 and U4 have not enough candidate vertices to be matched with because they have only candidate V1 which will lead to a conflict. So in this case, we simply filter out V3 from U2's candidate set, and we say V3 is not neighbor safe regarding U2. So this is necessary condition of an embedding. And the previous Sigmod paper proposes a uh, new necessary condition of an embedding, which is weak embedding, to get uh, complexes. And what we propose in this paper is to combine these two necessary conditions of embedding to get more complexes. So by using these two techniques in dynamic programming, we compute new uh, compact candidate set C prime new uh, in reverse topological order of query deck. So between this query deck and given CS, initial CS, we can get more complex CS by using this dynamic programming. And in backtracking, we need to decide our matching order. So So let's say we are just during backtracking, we are given a current uh, partial embedding, which maps U1 to V2, U2 to V5, and U3 to V6 at the moment. Then U4 and U5 are extendable vertices, and U4's extendable candidates are V2 and V9. So we select extendable vertex as the next vertex. But the problem is when there are multiple extendable vertices. So let's say we we just mapped U1 to V1, U2 to V2 in this example. But the problem is which quadrivertex should be mapped next in the matching order. So previous method commonly use select an extendable vertex such that its number of extendable candidates is minimum among non-degree one vertices. That is, they map degree one vertices as late as possible because degree one vertices have degree one and generally have a lot of candidates because their degree is low. So, but based on our observation, there are some cases that degree one vertices also have small number of candidates, and just always postponing these degree one vertices like U5 as late as possible may lead to huge search space of backtracking. So what we did is we first compute equivalent degree on query vertices with same label and with same neighbors. And we also compute uh, their unmapped extendable candidates. So if the number of candidates uh, are smaller, then we map these equivalent degree of vertices as early as possible. And in this search tree of backtracking, uh, we can imagine every partial embedding. So in this search tree, we map U1 to V1 first, then U2 to V3, and U4 to V8, and so on. And there are many equivalent subtrees uh, with similar failing in similar way like these. These two purple boxes are equivalent, and these two blue subtrees are equivalent uh, in terms of failing in a similar way, and so on. So, what the key idea of this pruning technique is to detecting these equivalent subtrees and pruning out them. For example, in this CS, for every quarter, uh, let's say we are given this CS, and for every quarter vertex and every candidate, its candidate vertex, we define a cell, which is a set of vertices that share neighbors. So for example, V3 and V4 in U2's candidate set share exactly same neighbors in CS. So they are in the same cell, which is depicted as a red box. And we also define equivalent set, which is a subset of the cell. So, uh, so the idea is that for equivalent vertices in an equivalent set, uh, these vertices mapping U to these candidate vertices may lead to an equivalent subtrees. So there are two cases of equivalent subtrees. For first, uh, sub equivalent subtrees may lead to no embeddings. So in this case, let's say we just uh, came to node U5 to V4 after exploration of this subtree, then uh, by the computation of equivalence set, we know V4 and V5 are in the same equivalence set. So mapping U5 to V5 will lead to no embeddings as well as in the previous subtree here. So we simply skip mapping U5 to V5 and backtrack to U3 to V9. At the moment, we also know V9 and V10 are the same equivalence set. So uh, mapping U3 to V10 will lead to no embeddings as in a previous subtree routine at U3 and V9. And so in this way, we skip mapping, exploring these gray subtrees, which will with uh, with no embeddings will be found. And second case is that equivalent subtrees with that leads to embeddings. So let's say we came back to node U4 and V10 after the exploration of this subtree, and in this subtree we generated two embeddings, and we have a V10 and V12 in the same equivalent set. So mapping U4 to V12 will lead to embeddings symmetric to the embeddings that generated from the previous subtree routine at U4 and V10. So uh, in in this way, we can get symmetric embeddings in a gray subtrees without exploration of these subtrees. So this uh, this is only applies to subgraph matching, which find all embeddings of Q in G. So for performance evaluation, we compared our algorithm back with state-of-the-art methods on many real uh, data sets. First, we measure false positive ratio of filtering of subgraph search. Uh, so we compare the filtering power of our filtering, every filtering technique of competing algorithms, and VEC is depicted as blue, black, black lines here, and uh, and as shown in these figures, back is shown to be back shows lower first positive ratio than others, which means better in filtering. And for core processing time of subgraph search, back is depicted as black boxes here, and as shown in these figures, back is shown to be faster in core processing, like more than 100 times faster than state-of-the-art method depth in IMDb, PPI, and Colab. For software matching, we first measure the size of auxiliary data structure, which means the sum of all candidates in every candidate settings auxiliary data structure. So the smaller the sizes, the smaller the such spaces. And back is more compact than others, the others up to 20% less candidates than depth. And in query processing time of software matching, back is also shown to be faster, like more than 100 times faster than GraphQL with valence set. In conclusion, our algorithms, we propose a new algorithm called back, which uh, uses three main techniques: extended dagger graph DP and matching order based on static equivalence, and runtime pruning by dynamic equivalence. And further discussion uh, like sensitivity analysis or effectiveness of individual techniques are described in performance evaluation of the paper. So please refer to our paper for more details, and thank you for listening.